Hello and welcome to another lecture of ECE 108. In this lecture, we're going to introduce the idea of the converse and contrapositive of a statement, talk about some of the algebra of the logical connectives we introduced in the last lecture, and introduce predicate logic. Okay, so let's jump right in. So the implication Q implies P is the converse of the implication P implies Q. Further, the implication not Q implies not P is the contrapositive of the implication P implies Q. So why do we care about these two particular implications? Well, the answer is the contrapositive gives us a new proof technique for how to prove a statement. And for any given statement, a natural first question to ask is, does the converse of the statement hold? So these two types of implications are commonly mixed up, so make sure you do not mix them up. So let's give an example of the converse and the contrapositive of a statement. Differentiable functions are continuous. So this is a true statement from calculus. If you're not familiar with this statement, don't worry, we're just using it as a placeholder example. So what would the converse of this statement be? Well, to find the converse, all we do is swap the order of the hypothesis and conclusion. So the converse of this statement would be that continuous functions are differentiable. So now, is this true? Well, from calculus, you'll know that this is in fact not true. A common counterexample is the absolute value of x. Okay, so contrapositive. What would the contrapositive of the statement differentiable functions are continuous be? Well, I want not q implies not p. So if a function is not continuous, then it is not differentiable. So explicitly, we get this statement here. So in this case, it turns out that this statement is true for the particular statement that we had here. And in general, the contrapositive is always true, while the converse of an implication may or may not be true. Okay, so another exercise. Use a truth table to compare the truth values of the converse and contrapositive of a statement to the original statement. A good exercise would be for you to pause the lecture now and try to do this on your own before I give you the solution. Okay, so here's the solution. So to build the truth table, we need the truth table entries for P implies Q. We need the truth table entries for the converse, which we can do trivially. And we need the truth table entries for the contrapositive, which means we need these two negations. So here I can notice that the contrapositive has the exact same truth table as the original statement. On the other hand, the converse does not always have the same truth values as the original statement. So thus, I can claim that the contrapositive is equivalent to the original statement, but the converse is not equivalent to the original statement. Be very, very careful in not mixing these up. It is a common mistake that first-year students make. Don't fall into that category. So theorem, any statement is equivalent to its contrapositive. The proof for this theorem is the truth table up here. This will come in handy next week, and it is a very strong tool when doing mathematics in general. Okay, let's give a couple examples. If A is less than B, then A is less than or equal to B. So is this a true or false statement? So take some time, think for yourself. Is it true or is it false? Well, it's a true statement, right? If A is less than B, then obviously A is going to be less than or equal to B because the conclusion is more strict than the hypothesis. Okay, so what would the contrapositive be? Well, I want to negate the conclusion. So the negation of A is less than or equal to B is simply A is greater than B. And then I want to negate the hypothesis. So the negation of A is less than B is A is greater than or equal to B. And then I swap their order. So this would be the contrapositive. So is this statement true? Well, yes, it's true. If A is greater than B, then A is going to be greater than or equal to B. Again, this statement is less restrictive than this statement here. What about the converse? Well, for the converse, I just want to swap the order of the hypothesis and the conclusion. So if A is less than or equal to B, then A is less than B. Is this true or false? Well, no, it's false. If A is equal to B, the hypothesis is true, but the conclusion does not hold. Okay, so what about this statement? For a real variable x, if the absolute value of x is equal to 3, then x squared is equal to 9. Is this a true statement or a false statement? Well, it's going to be a true statement. So the solutions here are plus or minus 3, and if I square positive or negative 3, I get 9. So this is true. What would the contrapositive be? Well, again, I want to negate both the hypothesis and the conclusion and flip them. So the negation of x squared is equal to 9 is x squared is not equal to 9, and the negation of the absolute value of x is equal to 3 is simply absolute value of x is not equal to 3. So is the contrapositive true or false? Well, it can take a little bit of thinking, but this is true. If x squared is not equal to 9, then that means x is not equal to positive 3 or negative 3. It can take on any other value, just not positive 3 or negative 3. Therefore, when I take its absolute value, there's no way it can be 3. Okay, what about the converse? Well, for the converse, I again just swap the order of the hypothesis and conclusion. So if x squared is equal to 9, then the absolute value of x is equal to 3. So is this true or false? Well, if x squared is equal to 9, I can take the square root and I get x is equal to plus or minus 3. And when I take the absolute value of that, I get true. So here we've seen an example where the statement and the converse have different truth values and where the statement and the converse have the same truth values. So do be wary when considering converses. The converse does not always have the same truth value as the original statement, but the contrapositive does. Okay, now on to something completely different. So previously, when you did arithmetic, so addition, subtraction, multiplication, division, you had certain algebraic properties that held. For instance, a plus b is equal to b plus a times b was equal to b times a, so the order of addition and multiplication didn't matter. We had some associativity rules where I can add things in different orders, and we had distributive rules. And when doing arithmetic, these algebraic properties were quite useful. So a kind of natural question that might come to mind is, do we have algebraic properties for the various connectives that we've defined? The answer is yes, and let's go through them. So we have some commutative laws. P and Q is equivalent to Q and P. Similarly, P or Q is equivalent to Q or P. It doesn't matter what order I use. So we also have some associativity laws. So P and parentheses Q and R is logically equivalent to P and Q, parentheses around that, and R. So similarly, I have the same type of law just for or instead of and. Okay, these are nice laws. What else do we have? Well, we have De Morgan's laws. I covered these previously, so I'm not going to introduce them much. But if I'm going to negate a compound statement, this is how I can do that. Further, I have some distributive laws. How does and interact with or? Well, P and parentheses Q or R is equivalent to P and Q or P and R. Similarly, I have a distributive law when I swap the order of and or, and it's what you would expect. P or this Q and R in parentheses is simply P or Q and P or R. Finally, we have some implication properties. So again, we've covered these before. So P implies Q is equivalent to Q is implied by P. And P if and only if Q is equivalent to P implies Q and P is implied by Q. Okay, so what these algebraic statements let me do is dramatically simplify the amount of work that I need to do to prove statements. So that's why I'm really introducing these algebraic properties. So a good example is to go through and prove all of these statements via truth table. So we've already proved this De Morgan's law, and we've already mentioned this implication here, and we took this to be the definition of P if and only if Q. But for the rest of these laws, I highly suggest you try to prove them via truth table. I could say put any of these on a midterm or a homework assignment. Okay, so now that we have these algebraic operations, we can prove things without a truth table. So prove that these two statements are logically equivalent without using a truth table. So how would I do this? Well, I start with the left-hand side, and I use my algebraic properties to simplify it into the right-hand side. So let P, Q, and R be statement variables. If I ask you to prove something, you need to explicitly define everything in your proof. So you do need to state something like let P, Q, and R be statement variables. Otherwise, you could lose some points for your homework assignments or on the midterm or final. This original statement on the left-hand side can be simplified by using my commutative laws. So why would I possibly want to do this? Well, on the left-hand side, I have P, Q, R, but on the right-hand side, I have P, R, Q. So at some point, I'm going to want to swap the order of the R and the Q. So I can do that right now just by commuting not P with R. Okay, what can I do next? Well, here I have two AND operators, and I ultimately need to turn one of them into an OR operator. Well, I also have this not on the outside of everything, so why don't I use De Morgan's law to change this AND to an OR? Well, to do that, De Morgan's law would give me not this, so not P, or not all of this, so not this statement here. So now what's the next natural thing to do? Well, here in this final statement, I want to have Q on its own. Here I have a not Q. So let's distribute this not amongst this. Well, how do I do that? Well, I use De Morgan's law again. So here I would get not R. This AND would turn into an OR. And then I would have not Q. Okay, so the next natural thing to do is to get rid of this not Q by using our rule for double negation. So here this not Q simplifies to be simply Q. So now what do I need to do? Well, I have this OR Q bits kind of down pat, but this statement is not quite there, right? I have the parentheses kind of in the wrong spot. So I can use my associative laws to move the parentheses, right? I have an OR operation and an OR operation, so I can simply change this to parentheses not P or not R, close parentheses, not Q. So now I have this exactly where I want it, and I have these two bits grouped together, but I want this not to be on the outside of the parentheses. How can I get that there? Well, I can use De Morgan's law again. So here, if I factor out the not, I would want not of this, which is simply P. I change the OR to an and not R would simply be R. So here, this is how I could prove a statement without using truth tables. So now, do keep in mind, if I wanted to prove this via truth tables, I could, but I'd have to have 8 columns of things to deal with. So if I ask you to prove a logical statement, and I don't explicitly say you need to use truth tables, you can do it this way. Okay, now let's talk about predicate logic. So in particular, I want to talk about quantified statements. So a quantified statement is a statement that has a quantifier, a variable, a domain, and an open sentence. So I have not yet defined quantifier. I will on the next slide, but let's look at a couple of examples of quantified statements before we continue. So for all real numbers, x greater than or equal to 5, x squared minus x is greater than or equal to 0. So in this case, the quantifier will simply be the for all. The variable will simply be x. The domain will be real numbers greater than or equal to 5, and the open sentence will be this element here. Okay, let's look at another example. There exists an integer n such that n squared minus n is equal to 0. So in this case, the quantifier will be there exists, the variable will be n, my domain will be integers, which I will denote by this z, and my open sentence will simply be this statement here. So with these examples in mind, let's explicitly define quantifiers. So the phrase for all denoted by this upside down A is the universal quantifier, and the phrase there exist denoted by this backwards E is the essential quantifier. So in this course, we're really only going to consider 2 types of quantified statements. The first type are universally quantified statements of the form for all x in S P of x. So here I'm jumping ahead a little bit and using set notation, but for all x in some domain P of x is true. And essentially quantified statements of the form there exists an x in S such that P of x. Again, I'm jumping ahead a little bit and using set notation, but there exists an x in the domain in question such that P of x is true. So let's look at a few examples of these type of statements. For all x in the real numbers, x squared minus x is greater than 0. This is a universally quantified statement. Is this true? Well, no, I could pick a value, say x is equal to 0.5. That's a counterexample for this statement being true. Another one, there exists an x in the null set such that x squared minus x is greater than or equal to 0. So here, I'm jumping ahead a little bit, but the null set is the set that contains no elements. So there is no x in the null set. So is this statement true? Well, the hypothesis of the implication is false, so this will be trivially true. How about this one? There exists an x in R such that x squared minus x is greater than or equal to 0. Is this true? Well, yeah, there's lots of values of x, so x is equal to 0 would be one example. How about this one? There exists an m in Z such that m minus 7 divided by 2m plus 4 is equal to 5. Is this true? Well, if I wanted to show if this is true, I'd have to solve for m. A good exercise would be to pause the video and solve that for m. And you find, yes, m is equal to minus 3 is an integer such that this statement holds. One more example. For all m in the natural numbers, m minus 7 divided by 2m plus 4 is equal to 5. That's a statement. Is this true? Well, no, because the only solution to this equation is minus 3. So if you're not familiar with these R, Z, in, feel free to ask in Piazza or office hours, but do keep in mind I will formally define them in a couple weeks, and I'm not expecting you to answer questions using these sets as of now. Okay, so a natural question I can ask is, can I negate these type of statements? So let's give a couple examples. Negate the following. Everyone in this room was born before the year 2010. What would the negation of this be? Well, it would be that someone in this room was born after or during the year 2010. So the opposite of this statement, that everyone was born before, is that someone was born after or during. So notice that I had to flip this everyone to a someone, and I switched the before to a after or during. Okay, so the absolute value of x is less than 5 for all real numbers x. What would the negation of this be? So I do suggest pausing the video and trying this now. Okay, so what is the negation of this? Well, x would have to be greater than or equal to 5. I have to swap this sign. Instead of for all, I need for some real number x. Again, I negated this statement here, and the for all turned into a for some or a there exists type statement. So next, someone in this year was born before 1980. So pause the video and practice negating this. Okay, so what would the negation of this be? Well, someone will turn to everyone. So everyone in this room was born after or during 1980. So again, the before switches to an after or during. Finally, x is greater than or equal to 5 for some real number. What's the negation of this? So pause the video and try. Well, the negation of this is that x is less than 5 for all real numbers x. So here you notice that the there exists turns into a for all when I negate the statement, and for all statements turn into a there exists. Additionally, less thans turned into greater than or equal to's. Befores turned into after or durings, greater than or equal to's turned into less than, and after or durings turned into befores. So can we formalize this idea for negating quantified statements? The answer is yes, and here's how we do it. So the negation of for all x and s, p of x, is the statement there exists an x and s such that not p of x. So an example of this would be this everybody, the for all in this room, turned into someone in this room, and before the year 2010 turned into its negation after or during the year 2010. Further, if I want to negate an essentially quantified statement, I would have that the negation of there exists an x and s such that p of x is true is for all x and s, not p of x. So an example of this is this someone in this room, this bit here, turned into the everyone in this room, this bit here, and the was born before 1980 turned into its negation. So finally, we can nest quantifiers. So let's examine all the possible nested quantifiers that I can have for two quantifiers. So for all x in R and for all y in R, I could have a statement like x minus y is equal to 1. So is this a true statement? We'll pause the video and see what you think. Okay, so this would not be a true statement. Why? Well, this is saying no matter what real number I plug in for x and y, it's going to be equal to 1. That's clearly not true. 0 and 0 are counterexamples. So next I can say there exists an x in R, and there exists a y in the real numbers, such that x minus y is equal to 1. So is this true? So pause the video and think about it a little bit. So yes, this is true. I could pick x is equal to 1 and y is equal to 0, for example. Next, I can mix the quantifiers. For all x in R, there exists a y in R such that x minus y is equal to 1. So what is this saying? This is saying for any given value of x in R that I give you, you can find a value of y in R such that x minus y is equal to 1. Is this true? So pause the video and think about it for a little bit. Okay, so yes, this would be true. For any given value of x, I could simply solve this equation for y and say y is equal to x minus 1. Since x is a real number, y would also be a real number. So this would be true. Finally, I can swap this order. There exists an x in R for all y in R such that this is true. Is this statement true? So pause the video and think for a little bit. So no, this statement would not be true. What this statement is saying is that I can find some value of x such that no matter what the value of y is, this statement is true. And that is clearly not true. So what's the lesson out of all of this? Well, order matters. So when I have two different types of quantifiers nested together, a for all and a there exists, the truth of the statement is dependent on the order of the quantifiers. Further, in these cases here, order doesn't matter because I have the same quantifier. Thus, in these type of cases, I can use a few shortcuts. So explicitly, this statement for all x in R and for all y in R can turn into the statement for all x and y in R. So I can only do this when the quantifiers are the same and the set is the same, or the domain is the same. Similarly, for there exist type expressions, there exists an x in R, comma, there exists a y in R, can simply be written as there exist an x and y in R, given that I'm using the same quantifier and the domains for x and y are the same. Okay, so that concludes the material for this week. You should read the material on pages 17 through 19. And again, I highly suggest you go through and prove some of the algebraic properties of connectives via truth tables just to get a bit more practice in. Next week, we're going to kind of turn ship a little bit and start examining proof techniques. The proof techniques that we discuss in the next week are built upon the logic that we've covered this week, so do make sure that you understand the material from this week. Otherwise, things can start to build up a little bit next week. As always, if you have any questions, feel free to ask on Piazza, or even better yet, come to office hours or tutorials. Have a wonderful weekend, and I will talk to you on Monday.